In the previous tutorial, we modeled contact using the contact pairs method. We identified the contact pairs, the surfaces likely to come in contact, and assigned interaction properties to each of these potential interactions. In this tutorial, we model contact a little differently using the newer general contact method. Consider the use of a crimp tool on a bunch of wires. If you wanted to simulate these wires coming in contact with each other, you'd need to create a contact pair for each potential contact condition. Since each wire might come in contact with a number of others, you would need to define a large number of possible contact pairs. In such a scenario, the general contact method would save you a lot of effort. In general contact, the analyst does not need to predict which surfaces may come in contact. Instead, Abaqus monitors the surfaces of all parts involved in the simulation and automatically detects contact between them. Therefore, you would only define general contact once in the simulation setup for crimping, and any contact interaction between any of the wires would be detected by Abaqus automatically. We will now demonstrate the general contact method by modifying the example from the contact pairs tutorial. To refresh your memory, we have three parts: a curved block, a rectangular block, and a plank. The curved block is fixed on the bottom, and the plank is fixed at one end, making it a cantilever. Two concentrated forces are applied on the free end of the plank, pushing it downward so that it bends around the curved block. At the same time, the rectangular block holds the top surface of the plank flat, preventing it from arching upwards. The dimensions of the parts are displayed in the figure. The plank is made of aluminum 2024 T3 with a mass density of 2,770 kilograms per meter cubed, a Young's modulus of 73.1 gigapascals, and a Poisson's ratio of 0.33. The rectangular and curved blocks are made of AISI 1005 steel with a mass density of 7,872 kilograms per meter cubed, a Young's modulus of 200 gigapascals, and a Poisson's ratio of 0.29. We will have contact in two regions. The first is between the plank and the curved block. We will make this interaction frictionless. The second is between the rectangular block and the plank. Here we will specify a friction coefficient of 0.1 and we'll tell Abaqus it is isotropic, meaning that the friction coefficient is the same in all directions. This means that we will first create two interaction properties, frictional and frictionless, just like we did in the contact pairs tutorial. However, we will apply them a little differently. We will apply frictionless as a global property. When this is done, all contacts detected by Abaqus's general contact algorithm are automatically assigned to the frictionless property by default. Individual contact interaction property assignments can be specified for surface pairs that should not use the globally assigned interaction properties. We will do this for the contact between the curved block and the bottom of the plank. Since we are only going to have contact in two regions of the model, essentially we will have made one contact interaction frictionless and the other frictional, thus creating the same setup we had in the contact pairs tutorial.